Hello everybody, my name is Iman. Welcome back to my YouTube channel. Today we're going to tackle a practice problem set that relates to our chapter 5 lecture on gases. Let's go ahead and get started with problem number 1. Problem number 1 says the pressure of a gas is measured to be 49 torr. Represent this pressure in both atmospheres and pascals. Okay, so this is great. We are given 49 torr and we want to convert it to atmospheres and convert it to pascals. Now, something that we know from our conversion table that we saw in lecture is that we have a direct conversion between torr and atmosphere that we discussed, right? We said that 1 atmosphere is equal to 760 torr. What we didn't talk about is a direct conversion between torr and pascal. So if we were trying to use the information we had to go from torr to pascal, we would actually want to maybe convert to an intermediate unit and then convert that to pascal. So we could essentially convert torr to atmosphere and then from atmosphere to pascal because we have that direct conversion. 1 atmosphere is equal to 101,325 pascal. Now, what this is telling us is that we should do the conversion from torr to atmosphere first, use our answer in units of atmosphere, and then directly convert that to pascal. That would be the easiest flow of things here. So that's exactly what we're going to do. We're going to write what we're given, 49 torr. We're going to go ahead and convert that to atmosphere using our conversion. That 760 torr is equal to 1 atmosphere. And notice we put torr in the denominator here so that the units cancel out and we get our answer in units of atmosphere. If you plug this into a calculator, you'll get 6.4 times 10 to the minus 2 atmospheres. Now we're going to take that 6.4 times 10 to the minus 2 atmosphere and convert it to pascal. For 1 atmosphere, this is going to be equal to 101,325 pascal. All right, atmospheres cancel out. We're going to get our final answer in pascal. Plug this into a calculator to get 6.5 times 10 to the power of 3 pascals. And there we have it. 49 torr is equal to 6.4 times 10 to the minus 2 atmospheres, and 49 torr is also equal to 6.5 times 10 to the power 3 pascal. With that, let's jump into example 2. Example 2 says sulfur dioxide, a gas that plays a central role in the formation of acid rain, is found in the exhaust of automobiles and power plants. Consider a 1.53 liter sample of gaseous sulfur dioxide at a pressure of 5.6 times 10 to the 3 pascals. If the pressure is changed to 1.5 times 10 to the 4 pascals at a constant temperature, what will the new volume be? All right, so what we're given from this problem is we're given an initial pressure and an initial volume. Additionally, we're given a final pressure, and our ultimate goal is to figure out a final volume. All right. Now, what's going to really help us here is remembering Boyle's law, right? We talked about the gas laws of Boyle, Charles, and Avogadro, as well as Gay-Lussac. We talked about Boyle's law, where Boyle studied the relationship between pressure and volume. And what he figured out is that pressure and volume have an inverse relationship. All right, there is an inverse relationship between pressure and volume. And from that discussion, we got a relationship between initial pressure and volume and final pressure and volume. Boyle's law can be written as P1 V1 equals P2 V2. And since we're given initial pressure 1 and volume 1, in other words, initial pressure and initial volume, and we're given final pressure, we can figure out final volume because we have 3 out of the 4 variables, which is all we need to solve this problem. So with that being said, let's actually write down what those values are. P1, we were told that this is 5.6 times 10 to the 3 pascal. right? We were given that here. And additionally, we were told that the volume is 1.53 liters. Then the pressure changes. We shift the pressure to 1.5. This is a 1.5 times 10 to the 4 Pascal. What is that final volume going to be? And we're going to use this relationship, Boyle's law, to solve for V2 by moving variables, all right, so that we have V2 equals something. And the way that we're going to do that is, I'm going to do some erasing here so we have room. I can show you how we are going to manipulate this equation. All right, we have P1 V1 equals P2 V2. We want an expression that says V2 equals something. We can do that by dividing both sides by P2. All right, that cancels out in this side, and what we get is that V2 equals P1 V1 over P2. And we have all these values, so we can plug them right in. P1 is 5.6 times 10 to the 3 pascals, and V1 is 1.53 liters, and then P2 is 1.5 times 10 to the 4 pascals. Notice units of Pascal cancel out, which means our answer is going to have units of liter, which makes sense because we're solving for a final volume. If you plug this into a calculator, what you'll get for V2 is 0.57 liter. The new volume will be 0.57 liter. With that, let's move into example 3. Problem 3 reads, a sample gas at 15 degrees Celsius and 1 atmosphere has a volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atmosphere? So what we're given here is an initial temperature and an initial pressure and an initial volume. Then we're given a final temperature and a final pressure and asked to figure out a final volume. Now, what we notice is that the initial and final pressures are the same. So what we're really dealing with is having an initial temperature and volume and trying to figure out a final volume while being given a final temperature. Here, Charles' law is going to be really important because Charles' law describes the dependence of the volume of a gas on temperature at constant pressure. We said from Charles' law that volume and temperature are directly proportional, and from that we can write the following expression. V1 over T1 is equal to V2 over T2. Now we're given V1 and T1 and we're given T2, and our goal is to figure out V2. So let's move around variables so that we have an expression that solves for V2. We want V2 equals something. So what we're going to do is we're going to multiply both sides by T2. And what we get here now is that V2 is equal to V1 times T2 over T1. Okay, so that's our expression. Now let's write down all the variables we know so that it can be easy to plug in. We're given that our initial volume is 2.58 liters and that our initial temperature is 15 degrees Celsius. Now this is in degrees Celsius, and in the lecture we made it clear that we want the temperature values to be in Kelvin. So we need to convert this to Kelvin, but that's really easy. All we have to do is add 273, and this gets us 288 Kelvin. Okay, fantastic. So now we have initial volume and initial temperature. We were also given final temperature. Final temperature is 38 degrees Celsius. We also need to convert this to Kelvin by adding 273. And what we get is 311 Kelvin. Now we can go ahead and plug things in. V1 is 258 liters. T2 is 311 Kelvin divided by T1, which is 288 Kelvin. And we notice Kelvin cancels out. We're going to get our final answer in liters. If we plug this into a calculator, we're going to get 2.79 liters. So there we have it. We solved problem 3. Let's go ahead and move into problem 4. Problem 4 says, suppose we have a 12.2 liter sample containing 0.5 moles of oxygen gas at a pressure of 1 atmosphere and a temperature of 25 degrees Celsius. If all of this O2 oxygen gas was to be converted to ozone, O3, at the same temperature and pressure, what would be the volume of the ozone? All right, so we're given some interesting information here. We're given an initial volume, we're given initial moles, we're given initial pressure, and we're given initial temperature. And then we're asked for final volume. All right, and we're also told that through this problem, through this reaction, temperature and pressure stay the same, which gives us a really important hint that moles is going to change. All right, our N2 is going to change. Now, if we know the reaction, which we do, right, we're going from oxygen gas to ozone, we can extract some really important information here, and that is what the final moles is. Why is this important? This is important because we're given initial volume and initial moles, and we can use this reaction to figure out final moles, which is really useful because we need these three variables to solve for final volume. How are we going to do that? Using Avogadro's law. Avogadro's law says that there is a relationship, a direct relationship between volume and number of moles, and we can write that law as V1 over N1 equals V2 over N2. But let's not get ahead of ourselves. Let's try to solve for N2 first, and then we can talk about using and manipulating Avogadro's law to figure out final volume. The reaction is going from oxygen gas to ozone. Now, this is not balanced, so we need to balance it. All right. We have oxygen gas, which has O2, and ozone, which is O3. Common denominator here is going to be 6, so we can add a 3 out front to the O2 and a 2 here in front of the O3, and both sides have 6 oxygens now, so it is balanced. Now, to calculate the moles of ozone, O3 produced, we can use the appropriate mole ratios from this balanced equation. So we can use mole ratios here to get N2. And the way that we're going to do this is we know we have 0.5 moles of oxygen gas to start with. We're going to do a mole to mole ratio. We know that there are 3 O2s to 2 O3s. All right. And that way, moles of O2 cancel, and we're going to get our answer in moles of O3. Plug this into a calculator, you'll get 0.33 moles of O3. So that means our initial moles is 0.5, our final moles is 0.33. Now we are also given initial volume, 12.2 liters, and our goal is to figure out V2. Like we said, we're going to use Avogadro's law, so we're going to move things around so we can solve for V2, and we can do this by multiplying both sides by N2. We'll get that V2 is equal to V1 multiplied by N2 over N1, and we can go ahead and plug those variables in because we know them. V1 is 12.2 liters, N2 is 0.33 moles, and then all over N1, which is 0.5 moles. You notice moles cancel out, liters is the remaining unit, so our final answer is going to have units of liter. If we plug this into a calculator, we're going to get 8.1 liter. And there we have it. We solved problem 4. Let's go ahead and move into example 5. This example reads, a sample of hydrogen gas has a volume of 8.56 liters at a temperature of 0 degrees Celsius and a pressure of 1.5 atmospheres. Calculate the moles of hydrogen gas molecules present in this gas sample. We have a volume here, a temperature, and a pressure, and what we're trying to figure out is number of moles. What we need to use here is the ideal gas law, which is PV equals nRT. When we have 3 out of these 4 variables, we can solve for the 4th, especially since R is just the gas constant. Now, we need to solve for a number of moles, so let's rearrange this expression so that we have N equals something. We're going to divide both sides by RT in order to do that, and we get that N equals PV over RT. Now, before we plug things in, let's just write down a list of what we know. We know the volume is 8.56 liters. We know that the temperature is 0 degrees Celsius. Now we need this to be in Kelvin. So what we're going to do is we're just going to add plus 273 to this. And what we're going to get is 273 Kelvin. That's the value for temperature that we want to use. We want to use this because our gas constant is 0.08206 liters times atmospheres per Kelvin per mole. So we want those units to match. We need our temperature to be in units of Kelvin. All right. Then we also have pressure. Pressure is 1.5 atmosphere. We're trying to figure out number of moles. And again, just as a reminder, our gas constant is 0.08206 liters times atmospheres per Kelvin per mole. Now we are ready to plug things in and solve for number of moles. Pressure, 1.5 atmosphere. Volume, 8.56 liters. Over our gas constant, which is 0.08206 liters times atmosphere, Kelvin times mole. All right, and then T is 273 Kelvin. What you notice here is that units of Kelvin cancel out. Units of liter cancel out. Units of atmosphere cancel out. We get our answer in units of mole, right? You see this, that this mole is in the denominator, right? So you might be confused how you get just mole and not inverse mole. Remember that this value is in the denominator and it is in the denominator of the units for the gas constant. So really, it's going to be flipped. So our answer is going to be in units of mole, which is exactly what we want. If we plug this into a calculator, we're going to get that our answer is 0.57 mole. And there you have it. That is example 5. Let's move on to the next problem. Problem 6 says quicklime is produced by the thermal decomposition of calcium carbonate. Calculate the volume of carbon dioxide at STP, that's standard temperature and pressure, produced from the decomposition of 152 grams of calcium carbonate. And we are given the reaction. So here we have calcium carbonate gives us quicklime and carbon dioxide. Now, the key to solving this problem is using all the stoichiometry tips that we've learned, specifically an important one we learned in this chapter, and that is the molar volume of an ideal gas is 22.4 liters when measured at standard temperature and pressure. And so we can compute the number of moles of calcium carbonate consumed and the number of moles of carbon dioxide produced just by taking advantage of some of these stoichiometry tips we know, mole-to-mole ratios, and of course, this molar volume of an ideal gas. Now, we're going to set this up starting off with what we know. What we're given is that we have 152 grams of calcium carbonate. And our hope is to solve for liters of carbon dioxide. So the first thing that we're going to want to do is convert grams of calcium carbonate to moles of calcium carbonate. Then we're going to do a mole-to-mole ratio so that we can go from calcium carbonate to carbon dioxide. All right, and then when we have moles of carbon dioxide, now we can use the molar volume of an ideal gas and use that to get liters of carbon dioxide because we know that the molar volume of an ideal gas is 22.4 liters. So let me show you what that workflow looks like. First step, we're going to convert grams of calcium carbonate to moles of calcium carbonate using molar mass. I'm going to go ahead and give that to you. You can calculate it very easily. 1 mole of calcium carbonate is equal to 100.09 grams of calcium carbonate. Wonderful. And that allows us to get rid of the units grams of calcium carbonate. We're left with moles. Now we're going to do a mole-to-mole ratio. This is a balanced reaction. We were given a balanced reaction. We're going to use our mole-to-mole ratios here to go from moles of calcium carbonate to carbon dioxide. It is a 1-to-1 mole ratio. So for 1 mole of calcium carbonate, we have 1 mole of carbon dioxide. Wonderful. Now that we have moles of carbon dioxide, we can use the stoichiometry, the gas stoichiometry relationship that we learned. For 1 mole of an ideal gas, carbon dioxide, and we know that that is the case because in the problem, we're told to calculate this at STP, standard temperature and pressure conditions. All right, so for 1 mole of this ideal gas, carbon dioxide, all right, that is equal to 22.4 liters of carbon dioxide. And notice how all of the units cancel out except liters of carbon dioxide. That's going to be the units of our final answer, which is exactly what we're trying to calculate. If we plug this into a calculator, we're going to get 34.1 liters of carbon dioxide. And there we have it. We solved problem 6. Let's go ahead and move into our next problem. Problem 7 reads, mixtures of helium and oxygen can be used in scuba diving tanks to help prevent the bends. For a particular dive, 46 liters of helium at 25 degrees Celsius in 1 atmosphere and 12 liters of oxygen gas at 25 degrees Celsius in 1 atmosphere were pumped into a tank with a volume of 5 liters. Calculate the partial pressures of each gas and the total pressure in the tank at 25 degrees Celsius. Now, we're given a lot of information here. We're given the pressure, we're given the volume, we're given the temperature. What we can do here is solve the number of moles of each gas just using the ideal gas law. Now, the ideal gas law is PV equals nRT. We can solve for the number of moles by shifting around variables where we get N is equal to PV over RT. We could solve moles for helium and for oxygen gas. So let's go ahead and do that first. For helium, we have pressure, which is 1 atmosphere, multiplied by volume, which is 46 liters, divided by R, which is our gas constant, that's 0.08206 liters times atmosphere over Kelvin times mole. All right, multiplied by temperature. Now, we're given it in degrees Celsius, 25 degrees Celsius. We can convert that to Kelvin by adding 273 Kelvin. You're going to get 298 Kelvin here. All right, plug this into a calculator. What we're going to get for number of moles of helium is 1.9 mole. Then we can do the same thing for oxygen gas, all right? Here we know we have 1 atmosphere. We have 12 liters divided by our gas constant, 0.08206 liters times atmosphere, Kelvin times mole, all right? And then temperature, we're given 25 degrees Celsius, add 273 to that to get it in Kelvin, plug this into a calculator, and what we get for number of moles of oxygen gas is 0.49 moles. Okay, fantastic. Now that we know the number of moles for helium and oxygen gas, we can start to solve and calculate the partial pressure of each gas. The tank containing the mixture has a volume of 5 liters and the temperature is 25 degrees Celsius. In other words, that's 298 Kelvin. And we can use these data and the ideal gas law to now calculate the partial pressure of each gas. So now for solving for the partial pressure of each gas, we need to rearrange this equation, the ideal gas law, to solve for P. We get that P is equal to nRT over V. So let's go ahead and I'm going to erase some of this so that we have room. All right, I'm going to erase some of this so that we have room to solve for the partial pressure, but I'm going to write to the side what we just calculated for number of moles. Number of moles for helium was 1.9 moles, and number of moles for oxygen gas was 0.49 moles. Now we want to figure out the partial pressure of each. Let's figure out the partial pressure of helium. We know the moles is 1.9 mole. We know the gas constant 0.08206. I'm not going to write the units. Actually, I will. I decided all of a sudden I will. That's atmosphere times liter over moles times Kelvin. All right, multiplied by temperature, 298 Kelvin, all over the volume, which is 5 liters. What we get for the partial pressure for helium is 9.3 atmosphere. And we're going to do the same thing for oxygen gas. It is 0.49 moles multiplied by the gas constant, liter times atmosphere over mole times Kelvin. We're going to multiply that by the temperature, 298 Kelvin, over total volume, 5 liters. What we're going to get for the partial pressure of oxygen gas is 2.4 atmosphere. So we figured out the moles of helium and the moles of oxygen. Then we use that to figure out the partial pressure of helium and the partial pressure of oxygen. And now we can figure out the total pressure by just summing the partial pressure. So 9.3 plus 2.4, that gets us 11.7 atmospheres for the total pressure. All right, so we calculated the partial pressure of each gas and the total pressure in the tank at 25 degrees Celsius, and those are our final answers. Wonderful. Let's move into our last and final problem. Our last problem says calculate the root mean square velocity for the atoms in a sample of helium gas at 25 degrees Celsius. Now, the formula for the root mean square velocity is that it is equal to the square root of 3RT over M. Now here, T is temperature. We're told it is 25 degrees Celsius. We want this to be in Kelvin, so we're going to add plus 273. And now we know that temperature is 298 Kelvin. That's the value we want to use. Now, R is our gas constant. And if you remember from our discussion on root mean square velocity, here we want the gas constant that has units of joules per Kelvin per mole, which is equal to 8.3145 joules per Kelvin per mole. And last, M is the mass of a mole of helium in kilograms. So we know that in grams per mole, it's 4 grams per mole. We just want to convert this to kilograms. So we're going to use a conversion factor. 1 kilogram is equal to 1,000 grams. And this gives us 4.0 times 10 to the minus 3 kilograms per mole. Now we have everything we need to plug into this equation. All right, so we're going to go ahead and just plug things into our equation. All right, we get that the root mean square velocity is equal to the square root of 3 times 8.3145 joules per Kelvin per mole multiplied by 298 Kelvin all over 4 times 10 to the minus 3 kilograms per mole. All right, and if we plug this into a calculator, what we get is 1.36 times 10 to the power 3, and the units here for root mean square velocity is meters per second. We're so finicky about the units we use for the root mean square velocity because, like we talked about in lecture, things are going to cancel out appropriately and we're going to get our answer in units of meters per second. And so the final answer here is 1.36 times 10 to the power 3 meters per second. And with that, we've completed our practice problem set. I hope this was helpful. Let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.